We have already analyzed steady flow devices. These are things like nozzles, pumps, and compressors. However, in this video, we will be looking at the influence of entropy on these devices. For a closed system, the moving boundary work is given by the integral of PdV. For steady flow devices, the first law of thermodynamics gives us this relationship. Where the heat in is equal to the work out plus the changes in all the other energies such as kinetic, potential, and enthalpy. However, we also know that the reversible heat input is equal to TdS, which is equal to dH minus VdP. This means that the reversible work is equal to the negative integral of VdP minus any changes in kinetic and potential energies. However, for the steady flow devices we have already seen, these are usually zero. Therefore, in these cases, the reversible steady flow work is equal to the negative integral of VdP. Note that this, with the negative sign, specifically refers to work out. For incompressible fluids, the volume is independent of pressure. In these situations, the integral is simply the specific volume times the change in pressure, P2 minus P1. If there is no work input from the surroundings, then there's only contributions from this pressure change and the changes in kinetic and potential energies. This yields this equation here, the specific volume V times P2 minus P1 plus 1/2 the velocities, V2 squared minus V1 squared, plus G times Z2 minus Z1 equals 0, which you may recognize as Bernoulli's equation. As a refresher, this is valid for incompressible fluids with no irreversibilities. Remember that irreversible processes use the least or produce the most energy. So the work input into a compressor is minimized when the process is reversible. One aspect of this is to remove all friction, make sure the compression is slow, etc. But there's another thing to consider. Looking at the equation for the reversible work input, the value of this integral will be smaller when the specific volume V is small. So another way to minimize the compressor work required is to use low specific volume fluids as the working fluid. These are generally liquids or low temperature gases. Like most devices, we like to compare steady flow devices to their idealized counterparts, and usually through efficiencies. However, just like other things we have seen, comparing it to 100% is not always the idealized situation. In these cases, it is the reversible isentropic process that are the idealized process. We can then calculate the efficiency of this isentropic process to have a benchmark to which to compare. This is sometimes also called the adiabatic or isentropic efficiency. Now looking at the various steady flow devices we have already seen, we can start with turbines. The inlet and outlet pressures are usually known, and there are usually only small changes in kinetic and potential energies. The energy out is given by the work produced by the turbine. In terms of the isentropic efficiency then, we should compare this actual work output to the isentropic work output. So for a turbine, eta sub T for turbine is equal to WA over WS, where the A and S subscripts refer to the actual and isentropic versions. The work output for a turbine is equal to H1 minus H2. H1 will be the same since the inlet conditions are the same, but the values of H2 will be different between the actual and isentropic processes, as can be seen down here on this HS diagram. The largest, most efficient turbines can have isentropic efficiencies above 90%. For compressors, we are mainly concerned with the energy input to the compressor. Again, we have specified values for the input and exit pressures. So here the isentropic efficiency is given by eta sub C for compressor equals WS over WA, or H2S minus H1 over H2A minus H1. Note this is opposite of the turbine, where it was energy out as opposed to energy in. Again here, well-designed compressors can have isentropic efficiencies in the 80 to 90% range. Pumps are very similar to compressors. The main difference is that they use liquids as a working fluid as opposed to gases in compressors. So the isentropic efficiency for pumps is the same as that of compressors. However, we can further simplify this case since we know that for incompressible fluids, the work input becomes simply the specific volume nu times the pressure difference P2 minus P1. Finally, we can look at nozzles. These accelerate the fluid, meaning this is one case where kinetic energy changes are important. The kinetic energy at the inlet is generally much smaller than that of the outlet. So the isentropic efficiency of nozzles is given by eta n equals V2 squared actual over V2 squared isentropic, just the ratio of the squared velocities at the outlet. Nozzles can have pretty high isentropic efficiencies and are commonly above 95%. We have now reached the end of this video, so here is a pre-lecture example related to these topics. As usual, bring any questions you may have to class later.